Hi everybody, we are now doing chemical equilibrium. Welcome to this e-recording. We have to do this video recording because of the fact that we can't have live lessons. Hopefully you're listening just as well. Heard that your Olympiad has also been postponed, but still learning never stops, right? Yeah. Okay, so this lesson is on chemical equilibria. All right. Okay, so basically you know that chemical reactions, there are irreversible and also reversible reactions. So for this particular chapter, we're going to look at reversible reactions. But first, a couple of examples for irreversible reaction, such as your reaction of carbonate with acid. So once you actually react calcium carbonate with acid together, you realize that the products that are evolved, they will not actually form back to get back your reactants. So this is one example of irreversible reactions. Okay, let's also now look at this graph of concentration versus time for irreversible reaction. Okay, consider this reaction A plus B to give you C plus D. At the end of this irreversible reaction, there's no more reactants A and B. All right, if of course, if they are added in stoichiometric amounts. All right, the concentration of the product will remain constant once the reaction has been completed. So you can see from this graph, concentration of A and B actually goes down to 0, while C and D actually increases until the reaction has completed. All right, so irreversible reactions are actually quite straightforward. You actually see these reactions quite a lot, like combustion. You see them around all the time. All right, once the combustion is finished, basically there's nothing left of your reactants. Okay, so now we come to the reversible reactions. Beg your pardon. Reversible reactions are reactions that does not proceed to completion. All right. In fact, there's many reactions that are actually reversible. Okay, so a reversible reaction is denoted by this sign over here. We call it the equilibrium arrow. So what this means is that while the reaction is taking place in the forward, all right, the forward reaction, all right, the backward reaction is also taking place as well. All right, so in this example, nitrogen and hydrogen combine to form your ammonia, but ammonia is also breaking down at the same time to form your nitrogen and hydrogen. All right. Okay, so this is what we call equilibrium. So this is a state where the concentration of the reactants and the products roughly stays the same. Okay, so let's look at a graph of concentration versus time, like what we did earlier. All right, you notice that after a while of reactions, right, your reactant does not go to 0. Okay, and they kind of reach a plateau where they will just have this same concentration for the rest of the reaction. All right, so this is what we call a dynamic equilibrium. All right, so where the concentration, they actually stays constant. All right, so typically it takes a while for a reaction to reach dynamic equilibrium. All right, this refers to a reversible reaction where the rate of the forward reaction is equals to the rate of the reverse reaction. All right, so let's take a look at the graph of rate against time. So earlier on we were looking at graph of concentration against the time. Now we are looking at the graph of rate against time. So there's a slight difference there. Okay, so you can see that actually the two graphs, right, they start to converge. All right, and when they are joined into one line, we say that dynamic equilibrium has been achieved. All right, so this dynamic equilibrium basically means that the reaction is ongoing, but the forward and the backward rate, the speed at which the reaction proceeds, they have become the same. All right, so the reaction is producing as much products as it is reactants. All right, so it's important for us to know this particular concept. Okay, so now we come to our first equilibrium constant that we're learning, is called Kc. All right, so when we consider these reactions, right, the reaction quotient Qc at any point in time can be expressed as here. All right, what you see. Okay, all the powers that is raised to, right, is actually your stoichiometric coefficient in the equation itself. Okay, the value of Q continuously changes with the progress of the reaction, all right, until equilibrium is reached. So at equilibrium, QC becomes a constant value called Kc. And it is important, it's vitally important for us to know that Kc is actually a constant at a fixed temperature. All right. So the concentration of A, B, C, and D has to be the concentration at equilibrium. Okay, so if we slot in those values at equilibrium, you will realize that your Kc, you will get the same value if the temperature is the same. All right, this is really just FYI. Okay, Kc can be represented by your rate constant as well. All right, so if you have learned your kinetics, you will realize that the small k of the forward over the small k of the backward reaction is actually equal to your Kc. Okay, this value of k, right, allows us to determine two things. Number one is your position of equilibrium. All right, like how much is the product in proportion to the reactants. All right, and the extent of the reaction. Okay, so when Kc is greater than 1, position of equilibrium lies to the right, and there is more products compared to your reactants. If it is equal to 1, the concentration of the products and reactants are around the same. Okay, if it's less than 1, position of equilibrium lies to the left, and there's more reactants compared to the products. Okay, so for reaction which involve gases, right, obviously they are all going to be in gaseous state. Our Kc can be represented in terms of partial pressure, and this particular equilibrium constant, we will give it a term called Kp. All right, it is the same thing as Kc, except that they are all given not in terms of concentration, but in terms of partial pressure. Okay, in case you've forgotten about your gases, how do we calculate partial pressure? It is to take the mole fraction over here, multiply by the total pressure. That will give you actually your partial pressure. Okay, so as this is like a e-learning, you should theoretically pause the video here while we do a quick check.